So to continue with where we left off last time, which was looking at the mechanism of how the esterification occurs. Remember, the overall reaction is that you have carboxylic acid react with an alcohol with an acid catalyst, you get the ester, and the byproduct is water. So the reverse of this reaction would be hydrolysis, in which if you take the ester and react with water in presence of acid catalyst, then you get the two parts back, which is alcohol and carboxylic acid, right? So we'll be looking at the reverse reaction in a minute, but I just want you to know that this is an equilibrium process, and usually in lab what you do is you push the equilibrium to the right by either removing the water once again or using a lot of alcohol, sometimes as a solvent, and that's usually how esters are synthesized. So for example, if you wanted to make the banana flavor or apple flavor ester, you would take the appropriate carboxylic acid and the right kind of alcohol, and you would run this reaction, and the whole lab will smell like a banana or whatever flavor that you're making. Okay, so same reaction occurs if you're doing an intramolecular esterification reaction, and the only reason I'm showing you this is because a lot of students get stumped when you're asked to do intramolecular reactions. So when you have a carboxylic acid and the alcohol all in one molecule is when this could happen, right? So here's an example. Here's a carboxylic acid, and then here's an alcohol, and you're going to do an intramolecular reaction. And any intramolecular reaction you do, as you know from sugar chemistry, 5 to 6 member ring was favored. So anything smaller or bigger is not going to be favored. All right, so here's an intramolecular OH perfectly set up to make the 6-member ring. So initially it's going to get protonated first and form the H plus, and then this alcohol is going to go and attack and open up the C double bond O double bond. So then you're going to form the 6-member ring with this carbon. So this carbon is the carbon of the carbonyl, which is why it has 2 OHs on them, one from the this OH and the other one from protonation of the double bonded oxygen. So then this oxygen that it attacked with is going to have the plus charge because it's got the extra proton. Then you're going to have a proton transfer to form the water. So here's the plus charge on the oxygen, and then then this pushes out the water. So water is formed. And you have the lactone forming at this point. Remember, that's the name for a cyclic ester. So then this extra proton is going to be regenerated by water. And so you have the lactone forming. And you got the hydronium ion. In other words, acid is regenerated. All right. So same chemistry, is just within the same molecule, right? So at this point you should be able to do these naming, and also couple the problems here. So make sure you do 12.12 FHI and then 12.13B. All right. So now we can move on to the reactions of esters, and they're basically 2 big reactions that you should be familiar with, and that is, one is the acid hydrolysis of the ester. So that's basically, like I said before, reverse of the esterification reaction that you saw in the previous page. So here you're going to start with, for example, an ester. So let me start with the Pacific ester, and then you are going to have an acid catalyst and lots of water. And once again, this is a equilibrium process, but you have a lot of water here, and one way to push the equilibrium to the right would be to remove one of the products, either the alcohol or the acetic acid, and then the equilibrium will be pushed to the right. All right, so that's hydrolysis under acidic conditions. You could also hydrolyze the ester under basic conditions, and that has a special name called saponification. All right, so this is hydrolysis of ester under basic conditions. Okay. Now, this mechanism is going to be obviously different than under acidic conditions because we don't have acid around. So you're not going to protonate it first. What's going to happen is because basic conditions is either sodium hydroxide often or potassium hydroxide. So you're going to have a base around. So here's an example of a base. And because it's a very good nucleophile, it's going to right away be able to attack the C double bond O and break open the C double bond oxygen to form this intermediate. So you're forming right away this oxygen carbon bond and form an O minus. And this is okay because we're doing everything under basic conditions. So O minus is going to be around it, and it makes sense that you have a negative charge species around. So that's gonna come down, and this time instead of kicking out the OH, which will be the reverse, it will kick out the OR group, and then you'll form this carboxylic acid, but that's going to be an intermediate and not what is isolated, because you have this OR minus around and OH minus around. And remember, carboxylic acids are acidic. Remember, the pK of this proton is around 5 to 6, 5 to 6, and these alkoxide and hydroxide ions are pK of like 16, so they're much more basic. So it's going to not stay around this acidic proton. It can't. It's going to be deprotonated, and it's going to form on so the alcohol is formed, and the final product that you get is a sodium salt of the carboxylic acid. All right, and this chemistry, the saponification reaction, is the basis of how soap is made. And your book has a very good a description of it in page 1002. You should take a look at it. But basically, what you're doing is you're taking the triester. So a fat is taken. So remember, fat is basically a triester. And you're doing a saponification reaction with either sodium hydroxide or potassium hydroxide. And what you're getting out is you have the glycerol as the byproduct, but you have 3 molecules of fatty acid salt. All right? And the way, the reason why soap works the way it does is because you have this long R group coming off of a carboxylic acid salt. So you have a dual property. You have a lipophilic or hydrophobic section, and then you have a section that's hydrophilic or likes water because it's charged, right? So like likes like, so like dissolves like. So this part will be attracted to water, whereas this part will be attracted to fatty, greasy stuff. So when you actually wash your hands, what's happening is, let's say you have a grease on your hands or in your clothes when you do laundry. So that grease is going to be surrounded by soap molecules, and it's going to form a micelle. So this is like a 1D, like a cut cross section of it, but think of it as in a 3D, like a ball. So inside that ball is a grease, and it's surrounded by this hydrophobic tail of the soap. And what's facing out is the hydrophilic, the carboxylated salt, which is negatively charged, and so it's very polar. And so it likes water, and so the water is now able to wash the grease away because grease is inside this micelle. All right. So quickly, I want to go over the rest of the reaction that ester goes through, which is substitution reaction again with amine. This we went over. This is hydrolysis under acidic conditions. This is saponification. Grignard reaction does the same exact thing as you saw with acid chloride and anhydride. Reacts with two equivalents of it. And the reduction with lithium aluminum hydride does the same thing, goes to the primary alcohol because it delivers 2 moles of hydride. The only new thing that you haven't seen is a reagent called Dibol, which is, you could think of it as a weaker reducing agent compared to lithium aluminum hydride. So Dibol is weaker reducing agent. So what it does is it takes the ester to aldehyde, and it stops there and not able to reduce the aldehyde to alcohol. So this is a very selective reaction, and the structure of the dibol, which your book has, which I don't think you're going to have to know, because whenever you have this above the arrow, you're going to see the abbreviation. The dibol basically stands for diisobutyl aluminum hydride, and that's think of it as the other mild reducing agent when you had the acid chloride and anhydride. So that's a specific reducing agent for just for esters in giving aldehydes and stopping there. All right. So that concludes this lecture, and because there weren't enough draw problems, I made up some of these, so you should be able to do all these, as well as 21.22 and 21.24 before you come to lecture. And if there are any questions, make sure you circle them and be ready to ask during class. All right, so this concludes the ester lectures.